8.1 Proof by induction. The basis of proof by induction is a four-step process. What we're trying to show is that we show that it's true for the first case, then we show that it's true for the following case, then it must be true for all cases. And that's the basis of induction. So I've got a little video here. You can link to that. I'd watch it after we finished. It would probably make more sense then. Okay, so this is what we're trying to do then. We show that if it's true for one case, and we can prove that it's true for the next case, then we can show it's true for every case. Our four-stage process is, first is the basis. So we say that n equals 1, and we prove it's true for the case n equals 1. Then we assume then the general case. We assume that it's true for n equals k. So the n's are going to be replaced with k's. This is more, it's easier to see when we do the example. Then we do another proof. Now we prove that it's true for the case, the following case, n equals k plus 1. And it will become clearer in the example. That's the inductive case. So the basis, n equals 1. Assumption, general case, n equals k. The induction phase, that n is going to be equal to k plus 1, the following case. And then the conclusion then. So we can conclude that if it's true for the first case, and it's true for the following case, it must be true for all cases. So you can pause and make some notes here. I remember this as writing this as basic. Basis, assumption, induction, and conclusion. So that's what I used to write at conclusion when I was in school, basic. Basis, assumption, induction, and conclusion. Pause it, make some notes. Not too many. I think you just need basis, assumption, induction, and conclusion. That's it. I will look at an example. So here's our example. Prove that for any n in the positive integers, the sum from 1 to n of 2r minus 1 is equal to n squared. So using basic, first step is basis. And we're going to prove that the case is true for n equals 1. So if n is equal to 1, well, then our summation becomes r equals 1 to 1 over 2r minus 1 is equal to 1 squared. So if we look at our summation, r is equal to 1, so 2 times 1 minus 1 is equal to 1 squared is 1, so that means 1 is equal to 1. So the statement is true for n equals 1. It's not the greatest for writing this. I'm not very used to it. Right, next is our assumption phase. So the assumption then is that it is true for n equals k. That's our general form. So if we go back to our summation, we replace all the n's with k. R equals 1 to k. That's 2r minus 1 is equal to k squared. So if we expand this, what we get then is we get when r equals 1, 2 times 1 minus 1 plus 2 times 2 minus 1. Oops, don't need the brackets there, but I've committed to it now. Plus 2 times 3 minus 1, and so on. all the way up to 2 times k minus 1. And that's going to be equal to, put brackets around that, equals k squared. So that gives us 1 plus 3 plus 5 plus 7 plus 2k minus 1. And that's equal to k squared. So that's where we are with the assumption. Now we move on to the induction phase. Not sure I'm going to have enough room on this page. So for the induction, we've got to prove that it's true for n equals k plus 1. So we take our statement, the summation, and replace n with k plus 1. Really not sure I've got enough room, but I'm going to try. So our summation goes from r equals 1 to k plus 1. We got 2r minus 1 is equal to k plus 1 squared. Right, so if we expand that, we have, as before, I'm not going to use a 1 and a 2 again, I'm just going to copy what I've got above there. When it's equal to 1, I get 1 plus 3 plus 5 plus 7 plus 2k minus 1 plus, now I've got k plus 1, so that's going to be plus 2 times k plus 1 minus 1, and that's equal to k plus 1 squared. Now, looking at this equation here, from 1, if I put square brackets around 1, up to 2k minus 1, that's what I had in the previous assumption, which we assumed to be true. We said that 1 plus 3 plus 5 plus 7 up to 2k minus 1 is equal to k squared. So I can replace this portion with k squared. Plus, if I expand that, I get 2k plus 2 minus 1 is equal to, on the other side, I've got k squared plus 2k plus 1. And if I simplify the left hand side, I have k squared plus 2k plus 1. So left hand side is equal to the right hand side. So I can now say, I'm going to have to write this over here. I can go to, so I've done my basis, which I had to prove, made my assumption, then I've proved the induction phase. So I've proved the basis and the induction, so I can conclude then that the statement is true for n equals 1. That's our original statement. And the statement is true for the next term. Call it case. Therefore, the statement is true for all n. for all n. Okay, so hit pause, make some notes, and we'll look at another example. Hopefully my handwriting will be a bit better in the next one. Okay, so here's our second example. Prove by mathematical induction that for all n in the positive integers, the sum from r equals 1 to n of r squared is equal to 1/6 of n times n plus 1 times 2n plus 1. Okay, so this is one of the formulae you have used. Hopefully you remember. So using basic, first step is the basis. I don't think I'll have enough space for this, but we'll try. Basis, prove this true for n equals 1. So I want to prove that it's true for n equals 1. That means we substitute 1 for n. So our summation goes from r equals 1 to 1, r squared, and that's equal to 1/6 of 1 times 1 plus 1, which is 2, times 2 plus 1, which is 3. So on the left hand side, you just got 1 squared. That's going to be equal to 6 over 6. So that means 1 equals 1. So the statement is true. It is true for n equals 1. Okay, so going by basic, our next step is to prove that this is true. Our next step is the assumption. Trying to save space here. And we assume that it's true for n equals k. So we substitute then. Our summation becomes r equals 1, and wherever we've got n, we substitute for k, r squared, which is going to be equal to, I'll put brackets as they have in the example, which is equal to 1/6 of n, or k as it's now become, k plus 1, and then 2k plus 1. Okay, so we start with when k equals 1, we got 1 squared, k equals 2, 2 squared, and so on. I'm going to put my dots now early, plus all the way up to k squared. That's going to be equal to, on the other side, what we've already got. I don't think we expand that out. 1/6 of k, k plus 1, and 2k plus 1. So we've got 1 plus 4 plus 9 plus 16 plus k squared is equal to 1/6 k, k plus 1, 2k plus 1. Okay, so that's our assumption. Now we move on to the next part of basic induction. And we're going to prove that it's true now for n equals k plus 1. K add 1. To prove this, then we can make our conclusion then, which is the final part. So, taking our summation takes us all the way up to k plus 1. So r equals 1 to k plus 1. and that's r squared. That's equal to a sixth. Now instead of n, we've got k plus 1. And then here we've got, instead of k plus 1, sorry, instead of n plus 1, we'll have k plus 2. And then in the third one, instead of n, we've got k plus 1, so it'd be 2 times k plus 1 plus 1. So, if you look at the left hand side and expand it out, using what we had in the assumption, our general form, we can say that we got 1 plus 4 plus 9 plus 16 plus all the way up to k squared plus k plus 1 squared. And that's equal to a sixth of k plus 1, k plus 2, and if we expand that out, you get 2k plus 4 plus 1. So you got 2k plus 2. So you get 2k plus 3 altogether. 2k plus 3. Yep, 2k plus 2 plus 1. So looking at the left hand side again, from 1 up to k squared is what we had above there, which we assume to be true. So I can replace from 1 to k squared with a sixth of k times k plus 1 times 2k plus 1. So let's do that. So that means we've got a sixth of k, k plus 1, and 2k plus 1 plus k plus 1 squared. That's equal to a sixth, k plus 1, k plus 2, 2k plus 3. Okay. So now, let's simplify the left-hand side. Taking the left-hand side and simplifying it. If I put everything over 6, then I've got k times k plus 1 times 2k plus 1. Now that's over 6, but I want to put this over 6 as well, so I've got to multiply this term by 6, so plus 6k plus 1 squared all over 6. Now I'm just wondering if I've got enough room to prove this. Let's put simplify left hand side. So I'm simplifying the left hand side, so I'm ignoring this right hand side for now, because I'm going to run out of room, I'm afraid. So that's going to be equal to, if I expand and simplify my left hand side, I've got, well, k plus 1 is common to both terms, so I take k plus 1 out, k plus 1, brackets, let's use square brackets to distinguish. I'm left with k times 2k plus 1 plus 6 times k plus 1. And close my square brackets, that's divided by 6. That's equal to k plus 1, which is part of the original. And in the square brackets then, I have 2k squared plus k plus 6k plus 6, all divided by 6. Which is equal to k plus 1, square brackets, 2k squared plus 7k plus 6. 2k squared plus 7k plus 6, which I can factorize. I'm running out of room fast. K plus 1, let's put that in brackets. And if I factorize that, I get 2 and 3. So k plus 2 and 2k plus 3 over 6. And just to check, that's giving me 2k squared plus 3k plus 4k, which gives me my 7k plus 6. So that's perfect. And this now is equivalent to my right hand side. I'm going to write that there. EQU went to the right hand side. So we've proved the case. So we can say therefore statement true for n equals k plus 1. So I've proved the basis that is true for n equals 1, and I've also proved it's true for n equals k plus 1, the next case. So I can conclude then, where am I going to put my conclusion? There. So I can say statement is true for n equals 1, as we did before. And the statement is true for the following case. Therefore, the statement is true for all n. For all n. Good. Hit pause, make some notes, and I'll attach some examples for you to do. So here are your examples. Exercise 8a. And we got up to 6 and 7. Have a go at a few of them till you're confident. Okay, good luck. I'll attach exercise 8a